Greetings, everybody. This is the third set of notes about rocks. It's the final set of notes about rocks, and it's called Rock Classification and Identification. Just like other sets of notes, for this video you should be writing everything down that's in orange text. And if you find that I'm going too fast, feel free to pause the video. And at the end there is a slide that contains all the information that you should have written down. So all rocks can be broken down into three categories: igneous, metamorphic, and sedimentary. But they can be broken down further into subcategories. Igneous rocks are either intrusive or extrusive. Metamorphic rocks are either foliated or non-foliated. Sedimentary rocks are all either clastic, chemical, or organic. And beyond the subcategories, rocks are identified based on their mineral content and texture. So when we're identifying igneous rocks, we take a look at the size of the crystals, the texture, and whether or not there's air bubbles. If the rock has small crystals or a glassy texture or air bubbles, it's most likely extrusive. Here's two examples. We have obsidian on the left, that's a glassy texture on an extrusive igneous rock, and we have pumice on the right, those are air bubbles in an extrusive igneous rock. Here's an example or two of igneous rocks with large crystals, coarse texture, and no air bubbles. We've got granite and rhyolite, both intrusive igneous rocks. And beyond the two broad categories, a good strategy for identifying exactly which igneous rock you're looking at is to look at the mineral content. So remember, a rock is a mixture of minerals, and the particular minerals present can lead you to the identity of an igneous rock, based on this chart on the next slide. So for example, peridotite and dunite are made of primarily olivine and pyroxene. Granite has mostly feldspar, quartz, and mica. And this isn't every igneous rock, but it's just some examples of igneous rocks that and the minerals that they contain. And there's a little bit of flow here. It's a little bit of wiggle room. On the left side of the chart, you have more felsic rocks. That means basically silicate mineral-based rocks. And on the right side, you have mafic rocks, which have a higher iron, magnesium, and calcium content. The ones on the right also have a higher melting point. When you classify sedimentary rocks, and we're going to talk mostly about clastic sedimentary rocks here. Those are sedimentary rocks made up of bits of other rocks. We identify them based on the type of sediment, which includes the mineral content, the grain size, how rounded the grain is, and how well sorted the sediment is. I'll talk about a little bit about what each of those things means. So a sediment can spend varying amounts of time exposed to water. Rocks are broken down by weathering and erosion, and that usually ends up putting sediments into a body of water. The longer sediments are exposed to water, the more they change. Water is constantly eroding and sorting sediments as it transports them from the continents to the ocean. And you can see the chart here. We go from angular grains on the left to well-rounded grains on the right. A younger sediment that has not been exposed to water for very long will have more angular grains and larger grains. These sediments also tend to be poorly sorted. So on the left side we have a newer sediment, on the right side we have a sediment that's been in the water for a longer time and it's more rounded. Here's some images of sorting. Well-sorted sediments are mostly the same size, whereas poorly sorted sediments are all different sizes. Sediments that have been exposed to water for a long period of time are more well-sorted. So an older sediment that has been eroded thoroughly, exposed to water for a longer period of time, will have rounded grains and smaller grains. These sediments also tend to be well sorted. So throughout the course of being transported in a stream and then to a river and then eventually to the mouth of that river where it meets a larger body of water like a lake or ocean, the sediments change as they move through the water. Um, they get more well-rounded and more well-sorted. So near the headwaters up in the mountains, you have poorly sorted, less rounded grains. And at the mouth of the river where sediments are deposited, you end up with well sorted and rounded grains. And smaller sediments as well. The larger things fall out of suspension earlier, and the smaller sediments are easier to carry downstream. So this question says, in which zone would we find sediment with the most angular grains? That would be near the sediment source, in the headwaters in zone 1. And then in which zone would the sediment be more well sorted? That would be down by the delta in zone 3. And the well sorted sediments have been in the river longer. So this is another place where the water cycle meets the rock cycle, the sorting of sediments. Which sediment grain has been in the river the longest? The well-rounded sediment. Here is a satellite image of, I believe that's the Mississippi River, where it meets the Gulf of Mexico. And you can see all that sediment that's just pouring out into the Gulf of Mexico. That's going to be mostly silty, smaller sediments, mostly the same size and very well-rounded. Joke time. Which rock group has 4 members but none of them sing? Drum roll, please. Mount Rushmore. Haha. All right, back to business. Breccia is a clastic sedimentary rock with angular, unsorted pieces cemented together. So you can see that the pieces that make up that clastic sedimentary rock are all different sizes and they have sharp angles. Conglomerate is a similar clastic sedimentary rock, but it has more well-sorted grains. They're not perfectly the same size, but they're closer to the same size and they're more rounded. Oops. So which of these two rocks would you think formed upstream and which one would you think formed downstream? Upstream being the headwaters and downstream being the mouth of the river. Well, the answer to that question is the breccia would be upstream and the conglomerate would be downstream. When we're talking about different kinds of metamorphic rocks, there are 2 types of metamorphism. There is regional metamorphism and contact metamorphism. Regional metamorphism happens over a wider area with high heat and high pressure and deep within the earth. Contact metamorphism happens over a small area with contact between magma and parent rocks near a pluton. A pluton is a magma chamber, and rock bakes near the magma. The magma doesn't melt this rock, but it's in contact with the magma, so it becomes metamorphic. So contact metamorphism is kind of like touching the lava, but it's not becoming the lava. Regional metamorphism is like over a wider area near deeper in the earth, and it has more to do with heat and pressure. And that's all for metamorphic rocks. So here is everything that's supposed to be written down for rock classification and identification. I just shortened the title to classification to make room for more of the notes, and I could fit it all on one slide. So pause the video here if you need to catch up. And feel free to email me if you have any questions.